right. Welcome to chapter 10, electric fields. Okay, so this is the next chapter that we're doing. Hopefully by now you've already had a crack at all of those gravity questions. And after electric fields, you'll have another video coming on magnetic fields. That's the end of the area of study. And considering I've put in like 1 million hours into preparing all of this, I don't think it's too much to ask that you guys have done your bit and actually watched and done the work. All right, I went and prepared, and by the time you watch this, this will be uploaded and ready for you to view as well. This is a help sheet that I created for electric fields and have scanned, which means it's sitting, no, that's not it. It is sitting here, and this is everything you're going to need to know to understand the interactions of charged particles with each other and the electric fields that they create. And I've tried to go through as though I had to sit the exam and include every part that I could think of. Of course, when you're doing your own work, you take this information, which is actually extremely spread out, and condense it so you can see there's a lot of information here that in reality I got this kind of detail because I actually went through and did all of the examples, all 68 examples in detail. Actually nearly all. Okay, there were a few very repetitious ones that I didn't bother with, but yeah, so I did all of the questions, and that's how I built this help sheet. This help sheet has pretty much every little thing that I needed to get through everything. So basically, we've already covered some of these fields and these field lines, these field diagrams in class previously, so this shouldn't be anything terribly new to you. You can see here that what we're talking about in this chapter is the effect that point charges have, not only on each other, but on the space around them, okay? So, for example, as we know, gravity field, this diagram here would be a great example of a gravity field. Here, I'll zoom in a bit so make sure you can see it. Of course, you should have already downloaded and printed this. The notes that we're going to go through briefly and then get really into the examples are coming up next. These notes will have arrived in the mail by now. If they haven't, text me and I'll make sure that I drop them off at your house. Okay, so there's no problem with that. All right. Okay. So as you can see, this diagram here looks a lot like what a gravity field line would look like. Gravity field lines always aiming in, and it's very similar to the diagram of an electric point charge that is negatively charged. You can see here there's a point charge that is positively charged, the field moves out, negative charge moves in. This is something that catches some kids out occasionally. If you look at this diagram, this one I chucked in from the memory of a question that I think I put out somewhere once, where the charge was doubled. For example, what effect on the diagram would that have? And you can see that what I've done here is I've kept the circle essentially the same. I've illustrated going from a charge of plus 1Q to a charge of plus 2Q. So all the field lines are in the same direction. You'll notice that the circle itself doesn't represent an actual mass of any kind. It represents a point charge. So it's essentially, the charge is concentrated at the very middle in sort of like, you could imagine, zero volume, okay? And so if I draw a circle to represent the point charge, which this is, then when I draw a circle to represent a point charge with twice the charge on it, I don't change the size of the circle. The circle stays the same. The field lines, however, I have doubled them, okay? Meaning that the charge is affecting the area around it with twice as much intensity because there's twice as much charge. All right, so that explains why I've gone from here to here, okay? Again, you don't need to change the size of the circle that you draw or any other weird thing that sometimes students do, okay? Now, the negative is exactly the same. If this was 2Q, then I'd have to do the same thing here and put a couple of negatives here, or write down that it's negative 2Q. 2-point charges, a positive and a negative, the field lines that affect them, okay? You can see between these two, they are the field lines moving out from the positive charge and into the negative charge, very much like a dipole, as in two a north and a south pole. It's the same diagram essentially, that demonstrate the field lines. And then you've got the field lines moving between two like charges, as in two north poles or two south poles, and two like charges being negative. So in the positive, the field lines are always moving out, and in a negative, they're always moving in, but they have the same effect on each other. They don't want to be anywhere near each other. Okay? And then there is one more example which goes through and explains what the field is like between two charged plates. And the two charged plates, you have this is a standard diagram that you'll see in the notes as well, where there's a battery connected to two steel plates. The positive terminal charged connected to one and the negative to the other. So you've got a positive to a negative, and you've got an equal distribution of field. Okay, so the field is not any stronger on one particle to another, or in one position to another throughout here. When it says a uniform distribution of field strength, that's what it means. It is uniform everywhere in here. Does that mean, though, that if I put a proton in here, that it will be affected the same anywhere that I put it inside that field? Well, it doesn't really mean that, no, because if I put in, say, a proton into this space here. Now, I say a proton because I assume you remember Year 7 science, that a proton has a positive charge, okay? So if I put this positive charge in here and move it from the middle to the upper plate, obviously the proton is going to not really want to be anywhere near that positive plate because it is positively charged. It's going to try and get away from it. Likewise, if I move it towards this part of the plate, okay, well then yeah, it's going to really want to be there. It's going to be very easy to move a proton towards this part of the plate. So what that's telling me is, yes, the field is uniform throughout, but its effect on objects in the field isn't exactly uniform, all right? And if I chuck, say, a neutron in here that has no charge, it's just going to completely ignore everything that's around it, okay? So that's just a little bit of an explanation on the charged plates and how they really operate, okay? Important to keep that in mind because some of the questions that you get asked depend on that knowledge, okay? Now, so I've gone through and put down a bunch of information that comes through, that becomes necessary to answer a lot of the work that you're expected to do. Okay, so here we have electric field stuff. I've tried to concentrate mostly around here. So the electric field depends, the electric field strength depends when it comes to these plates. So this formula here is specifically for the calculations of these plates here. So, for example, you'd be given a certain voltage and a certain separation. So there's the voltage and the separation. Notice that, as usual, I use a really big V for voltage and I use a really small v for velocity. Okay, so I got into that habit early on to get rid of a lot of confusion. Okay, so anyway, go back to these electric fields. Electric field between the plates, all right, the field strength is equal to voltage divided by the distance. So whatever the potential difference between these two plates is, divided by the spacing. Now, the potential difference is in volts and the spacing is in meters. It is rarely given in meters in questions. They always give it to you in millimeters or centimeters. You really need to notice that, okay? If you don't notice that, then you automatically lose marks for simply not converting a really simple unit that all of you can do, all right? So make sure you notice that's in meters, that's in volts. Now, something else that may come up as you go along is electric field strength has an equivalent unit. It's not just in volts per meter, it is also given in newtons per coulomb, okay? So newtons per coulomb is an equivalent unit to volts per meter. So if you see either one of these, what they're talking about is electric field strength, okay? in between two plates. Okay? So that's really, really important. More electric field stuff here. E is equal to kq over r squared is the electric field strength around a point charge. Okay, so yeah, all right. So that information's there. F, as usual in physics, F is almost always force. All right, and so that's the other part of the equation, or the other set of equations. What I've done here at the very top is I've included all of your sort of standard values that apply in all questions in all areas that you study. So things like what the elementary charge is. Okay, so the elementary charge is the charge on an electron or a proton. Okay, so they are equally charged, except that one's positive and one's negative. Hence, if I'm writing down the electric charge on an electron, I put a little negative on there. Okay, it is charge. The units of charge are coulombs, so it's big C right there. And this one is specifically on the electron. Okay, so a couple of other values that they throw in, because in this unit we absolutely love linking forces, accelerations to particular particles, for example, to electrons or protons or even alpha particles. If you remember, hope you remember what an alpha particle is, just the nucleus of a helium atom, 2 protons and 2 neutrons. So things, those masses become important. So you've got the mass of the electron, 9.1. Often you see it quoted as 9.1 by 10 to the negative 31, and often as 9.11 for that little extra bit of accuracy, okay? But I tend to just chuck in 9.11 whenever I'm doing calculations. The mass of a proton and the mass of a neutron, they are almost the same. One is actually a little bit more massive than the other, but way past these decimal points, okay? So they are essentially the same mass. Okay, now K is a universal constant. It is a constant that links the force that acts on 2 charges. Okay, whether they're both positive, both negative, or one is positive or negative, that doesn't matter. But K is the constant that links the relationship between force and charge. Okay, and so that's what K is, and you'll see it being used a lot later on. And I then, as an afterthought, tried to cram in a few extra little things in here. 1 volt is equal to 1 joule per coulomb. So a volt is much like a Newton. It's not a real unit. It's just an abbreviation of a proper unit. And so the proper unit for voltage is joules per coulomb. What that really means is how much energy is being transferred per coulomb of charge. Now, you know that one elementary charge, okay, so the charge on an electron is 1.6, 1.6 by 10 to the negative 19, okay? So that is a tiny amount of charge on an electron. So to make up an entire coulomb of charge, a whole coulomb, you'd need to, there'd be a lot of electrons that would make that up, okay? Now, I've thrown in this little list here for you, which it's in purple. I'm starting to really love my coloured pens here. F is force, and this is another little thing that I really like you to do is when you're putting things down, little notes for yourself, make sure that every part of that information is there. So for example, F is force, okay, force on the charge, which is generally force, and it's in the unit N, newtons, okay? So put that there because it helps you when you're starting, if you happen to get lost, in the completion of a question, you go, oh, what was I actually looking for? What was this big U here for? I mean, I'm not really used to using U in electricity. It's like, oh wait, it's potential energy. Oh, it's in joules. Okay. All of a sudden, you found where you're supposed to be at. All right. So again, over here, I've noticed that throughout the questions that you're expected to do is Q, big Q, little q are pretty much used interchangeably. Okay. In a lot of questions, a lot of solutions, you'll see them using big Q or little q. They'll sometimes use, you can use Q in a question, or you might see them using Q and little q to denote that those 2 charges are not the same, they're not equal. Sometimes you'll see them using Q1 and Q2, or little q1 and little q2. It's Q, it's charge. That's all it really is, okay? So you don't need to really, don't get confused over that. It's just, physics is old, and lots of different people have contributed to it over the centuries, and hence lots of people write things the way they want to write them. And a whole bunch of conventions have grown up out of it to try and standardize things and make it easier to study, but some of these things still hang on, all right? Okay, so now these formulas are pretty important, okay? They are going to allow you to do a whole bunch of work through here, which I know you just can't wait for, okay? So the force between two charges, it doesn't matter if it's an elementary charge or if it's a collection of charges. The constant, the constant that links the relationship between force, charge, and the separation of those charges is F equals KQ1 Q2 divided by R squared. Be really careful, don't forget to square the R, all right? A lot of people even write it down and then fail to actually do it in the calculator. I know I've said that before, but it happens, it's irritating because you're losing marks for nothing, all right? Okay, now I wanted to put these two together. I found that when I was going through the notes that neither one of these formula were really used in any way in this, if I remember correctly actually, in the solving of any of these questions. However, they do help build a bit of understanding, because there is one question that you need to do early on that really does make use of this electrical potential energy formula here, okay? And so what I've got here, there's a difference between this and this, okay? So what this formula gives you, and you've got our nice traditional U that we use to denote potential energy, is the potential energy between two charges. Now this is just potential energy, okay? So in other words, I grab two charges, and let's say they are a positive and a negative, and I hold them at some distance apart. Notice the formula is almost identical, except you don't need to square R to actually calculate the potential energy. Now this would have been the result of some derivation, but we won't go into here because I don't believe this is even in the study design. So, however, if you take two charges and hold them at a certain distance apart, they will either attract or repel each other depending if they're like or unlike. And so they'll have a certain potential energy that is required to bring them there, to actually put them where they are, so they are under each other's influence in some way. So whatever that is, if you want to know what that energy was to put them there, you'd use this formula, okay? And so that is potential energy between two charges, okay? Now, even though that's not actually very useful to you in this unit, this one is a little bit more useful. This here is the electrical potential energy. Okay, the electrical potential energy is a different thing, okay? This is calculated in either volts or joules per coulomb. So this gives you the energy per coulomb. The energy contained in every coulomb of charge that you have, okay? So this is a different thing, because this is kind of like almost like a rate of energy where, you know, if you have more coulombs, they'll have more energy. And this is the very definition of what voltage is, okay? So when you see questions on the electrical potential energy, they're actually saying voltage, okay? And this becomes useful in understanding the question that's later on, okay? Now, the next few things that are important here is the work done, all right? These are the work done formula, and you can see that I've tried to make it as, as clear as possible. I was about to use the word unconfusing. All right, as clear as possible. Work done is always energy. You should know that now because we've visited that idea lots and lots of times, okay? It is measured in energy, work done is energy, and if I take an electron and accelerate it through a voltage, an electrical potential, it will take on kinetic energy, okay? So the work done on that electron as it's shooting through a set of charged plates is the energy that it has gained. And that's why I've gone through here and I've linked work done, okay, is equal to Fx, which is really kind of one of your kinematics things that we've been using, so just standard mechanics, right? which is equal to the big V, voltage multiplied by the charge. So yes, you take one electron and accelerate it through 1 volt, it picks up 1 electron volt of energy. Okay, now the electron volt is a equivalent sort of, it's an equivalent unit to joules, except that it's a non-SI unit, and we may have already discussed this in the past, I'm not sure, but and picking up 1 electron volt of energy simply means that you would take, to figure out what that was in joules, is you would just simply go 1 volt multiplied by the charge on the electron. Here it is, volt by charge on the electron. All right. So it will be 1 times 1.6 by 10 to the negative 19 coulombs would give you 1.6 by 10 to the negative 19 joules of energy. That's how much energy an electron will pick up if it is accelerated through 1 volt, a 1 volt field. Okay. So once you've got that, your head around that, the work done, again, this is the same formula quoted a little bit above here, where you pick up this energy. Okay, the work done, this is the energy an object will pick up as it's moving through. Okay, now, work done is also equal to QED. Don't forget what E is. E is electric field strength. What is electric field strength? It is V on D. All right, so you can actually, if you substitute V on D here, you end up with QV back here again, because those two D's cancel out, okay? But if you mucked around with it yourself, you'd see that pretty easily. All right, now, kinetic energy is equal to, as usual, mv squared on 2. Don't forget that electrons and protons and alpha particles all have mass, which means if at any point you are asked, and you will be, to calculate the final velocity of an object, of one of these particles after it's been accelerated, after a certain amount of work has been done on it, then you need to solve, you'll need to solve for velocity to figure out how fast that object is, and you'll need to know the mass of the electron or the mass of the proton or whatever it is that they've given you, which is why I quoted them way up there. All right? Now, the last part of the help sheet, F equals ma, which is mg. Okay, now here, this is, I think the last thing I wrote on here, the most confusing, because you see here we have work done, and I've been careful to write down work done rather than just W, which they often did in the notes. When you see a W, what we're really looking at is the weight, okay? A W on its own, when I'm doing this, okay, a W on its own is the weight, okay? It's similar to, weight equals mg, all right? The weight of an object. If you see W, that's what that is. But I've gone through and put WD for work done, which means that's not true, all right? So work done is a different thing to just W, which is weight. Work done is in joules, weight is in newtons, all right? So that can be a bit confusing if you're not looking out for it. Okay, let's have a look at their notes and see what we can pick up from those. Electric field notes, they've gone through the study design. Here are all the formulas that they kind of give you right at the start. Conductors and insulators. There are a series of YouTube videos which you really need to watch because they are incredibly helpful. I know some of you, if you remember Hewitt-Druitt, there's a bunch of Hewitt-Druitt videos which are really good and funny. Conductors and insulators, we'll start with this. A conductor allows the flow of electrons through the material. Metal is a good conductor of electricity because the structure of metals is such that the outermost electrons are free to move around in the fixed crystal lattice made up of the atoms. So in other words, a metal lets its electrons go more easily than a non-metal, and hence it allows a flow of electrons, which is electrical current. Electrical insulators do the opposite. Semiconductors will be something that we study in a little bit more detail a bit later. Semiconductors are like silicon. Your computer's full of semiconductors where they conduct and then don't conduct depending on what conditions they're put under. All right, so resources. Watch all these videos, they're grouse. I added one. If you look at your notes, this one's not in there, that's why it's 3.5, okay? Because I scanned and uploaded them for you, and then I printed them for you as well and sent them to your house before I chucked this in, okay? So I went through a lot of videos making sure that everything made sense and it was I could get enough detail to make sure that I'm doing this video for you that there weren't any confusing bits. All right, so this one's a good one, Coulomb's law. Okay, you should watch all of those videos, and I've left it up here on screen long enough for you to have a look, and you can pause and go, oh, type it in, open up a separate window, type them in, have a look at these videos. You have a look at the videos, you can look at them before you do the work, okay, and you'll see, oh yeah, so it'll kind of make sense. And then once you've done some of the questions, you'll find those videos are even more, they make even more sense. All right, so EMF and electrical potential, okay, that's just another word for voltage, okay? So if charges are moving, they have energy. A battery or generator is the usual source of this energy. When electrons flow through a battery or other power supply, they gain electrical potential energy. As the electrons flow around the circuit, they lose this energy when passing through components that have resistance, i.e. globes or any kind of machinery. Okay, so the energy transferred to 1 coulomb of charge within the battery is called the electromotive force of the battery. So the energy transferred to 1 coulomb of charge, see, that is the whole joules per coulomb. That's what a volt is, okay? So if you give 1 joule to a coulomb of energy, then it's a 1 volt battery, okay? So the unit of electromotive force, or EMF, EMF is the volt. EMF can be considered as a concentration of charge. The work done in pushing the charges together is stored as electrical potential energy. Basically, the idea is all these electrons that are squeezed together in one end of the battery, they don't want to be there. They're just, you know, they're too much of the sameness around them. They want to go out and explore and see what else is out there. And so they push apart, and that is that potential, electrical potential that we talk about, and that's the voltage, okay? So the work done in pushing charges together is stored as electrical potential energy. A battery with an EMF of 6 volts transfers 6 joules of energy to every coulomb of charge. Okay, now a coulomb of charge is like, I wish I'd written it down, I totally forgot. If you can pause for a second and go look it up. It tells you how many actual, you can look it up, how many actual electric charges make up a coulomb, and it's lots, okay? Which means 6 joules spread out along lots is not a real lot of energy in reality, okay? Which is why you can muck around with a battery and it's not going to shock you to death, all right? Because the amount of energy it actually gives you isn't very much, all right? So, the unit for potential, I've already gone through this. The term EMF and PD are often simply referred to as voltage. So, EMF and electromotive force, PD, potential difference, same thing, okay? Now, joules per coulomb, okay, the SI unit for electrical potential is joules per coulomb. This is given the name of volt after Alessandro Volta, who did all of this early work. I think we mentioned it in class once. The inventor of the first chemical battery. All right. Okay, so electrical energy. Okay, here this is, again, electrical energy. Again, they've used W here. All right, I would say, you know, WD, work done, or yeah, to make sure that you don't mistake that for weight, okay, since that does become part of all of your work. There's a whole bunch of stuff here which so work done is QV. This is actually on your formula sheet, just not with a lot of capitals, okay, so we've already covered that. If Q of charge passes through a potential difference of V, the work done, see, that was what I was talking about earlier, the amount of kinetic energy you actually gain. So if it takes V joules of energy to get 1 coulomb of charge from one place to another, then it takes VQ joules to get Q coulombs, yeah, whatever. And none of that's enormously useful anyway. Except the one maybe here. All right, so this is charge is equal to how much current, so the current, that's I, is traveling over how, so this is, amps seconds, all right? Again, not particularly useful in answering anything in this chapter. All right, Coulomb's law for point charges, all right? So again, imagine the charge as not being a sphere or a big ball or something, it's just a dot that has a charge on it. Its volume, even its mass, have no real bearing on any of these calculations. So the force of attraction or repulsion, this is the thing, if you've got, with gravity, it's always attractive, but with magnetism and with electricity, likes repel, and yeah, different charges attract. And that's really important in which way the force is actually going to be. Are these two Qs going to be attracted? Is the force going to be an attractive force, or is it going to be a repulsive force, depending on if they're both positive, both negative, or one's positive and one's negative, all right? Okay, where F is the force in newtons, Q1 and Q2 are measured in coulomb, R is measured in meters, then K is equal to 1 over 4 pi E naught, where E naught is the permittivity of free space. Okay, so this is actually this, and then this is the first and last time you'll ever see this unless you go off and do physics. Not useful, very useful. That's why it's on your help sheet. Okay, electric fields, it goes through all of these, everything that I've already covered, basically, in electric fields around a point charge. All right, so combining F equals KQ and R squared. See, here's another version of the formula that I mentioned earlier, big Q and little q, just saying that those two Q's don't have to be the same. Okay? And F equals EQ, so electric field multiplied by charge. For a point charge, Q given E equals KQ over R squared. The units are newtons per coulomb. So this is another electric field formula. This is the electric field due to a single point charge. So if I want to know what the electric field is, if I have a point charge that is positive and I know that it's, say, one elementary particle, say it's one proton, and I want to know, well, what's the field strength of this proton, I don't know, here, somewhere out here. And we're going to say that that is, I don't know, 0.5 meters away, just because, I don't know, I haven't really thought about doing this. So, in other words, how strong is the field out here? Okay, now out here is just this point of empty space. It's not like I've put another charge there or something like that. The field density goes down, inverse squared law, don't forget that, that's like really important as well. So it gets really intense, it gets more and more intense much more quickly as you approach, all right? Then it's not a linear relationship is what I'm trying to get at. All right, so if I want to know what the field strength out here is, I need to know what the charge is, and I need to know how far away it is in meters. So what the charge is and how far away it is in meters multiplied by K, which is standard value. All right, so this tells me what the electric field is somewhere or at any distance away from a particular electric charge. Okay, the direction of the field, that's a different thing. It's the same density or the same strength, or whether it's positive or negative, it doesn't matter whether it's positive or negative. What matters is how strong is the original charge and how far away from that charge are you, okay? That's all that matters there. Why did I screw up my paper when I need it to be my duster, since there's never a duster in these rooms? There we go. All right, so that is, yeah, that's that. Electric forces. Electric forces are given by the product of the electric field and the quantity of charge. So the force is equal to QE, okay? Don't forget E itself is also, so the force is equal to QE, but don't forget that E itself is actually V on D, all right? So you can substitute that. So force can be QV on D as well. Okay, that should be on your help sheet somewhere. It does not appear to be, but that's okay. It's there now. Write it down. Okay. It's almost impossible to look at. Now, why does this happen? Okay. It's almost impossible to get every iteration, every little combination of every formula that you need. So all you can do is your best, and the way you do try to nail them all is by doing all of the questions. Again, no way around that. Okay, you just really need to do all of the questions. Okay, electric fields between charged plates. We've already discussed this in relation to the help sheet. It was all there. I put in a whole bunch of extra information there to make it easier for you as well. So I'm not going to go over that again. Videotape's not cheap, you know. Alright, so electrical potential energy, again, went through all of this already. The only thing, okay, Did we mention circuits specifically? When the elements in the circuit are in series, okay, there is one question in the examples which does make a relation to this. They all have the same current. The potential drop across each element is proportional to the resistance. You know that already, it's just V equals IR. If the resistance is 0, then the part of the circuit is an equipotential, i.e. there is no voltage drop, okay? So yeah, that means and that only occurs in superconductors where there's no actual drop. So the electric field in a wire is given by change in voltage over D. So this is important, as in the electric field in between two plates, all right, is calculated by V over D, all right? But let's say in your near future, you see there's a question that has, say, 3 bits of wire, and the 3 bits of wire separated in that 2 bits are twice the resistance than the one that connects them, okay? So essentially it's like 3 different resistors in a row, okay? What is the field strength? What is the field strength near a particular wire? Well, you can treat the wire as though it's parallel plates. You know the voltage that is dropped across that wire from that section, and the distance away from that wire that you are. It's the same, it gives you the same value. It's treated the same as though, because when you look at these charged electric plates, they have that field that's going through the middle, as shown in the diagram. Well, they actually do have field extending the other way as well, okay? Because it's basically 2 separate fields, as though each plate is like a wire, okay? So it has a field extending in both directions. But when we do these questions, we basically concentrate on the field in between the 2 plates, not worrying about what's happening on the outside, okay? So don't get all like confused by that. Millikan's experiment. This is probably the last thing. Millikan is the dude who basically did a lot of the first work in finding what electrical charges were, okay? So remember, if you remember correctly, we talked in class about how there is an elementary charge. In other words, Millikan is the one who did the work to try and figure out, can you divide charge infinitely? And he found, well, no, you can't, okay? And that's where we get the 1.6 by 10 to the negative 19 coulombs. So we say, okay, electric charge is measured in coulombs, and if you take 1 coulomb, you can divide it down into a specific number of individual charges, and they will all be the same. Okay, so if they're all the same, it means that you can get down to 1 elementary charge, which is indivisible. So you can't get a charge smaller than 1.6 by 10 to the negative 19 coulombs, because that would be basically impossible. There's nothing to attach that charge to. The electron, being a fundamental particle, is at the lowest charge that it can be. Okay, so Millikan kind of proved all of this and did a bunch of experiments and maths. It was a very cool experiment. I'm not going to pretend to remember every detail. Basically, firing between 2 charged plates in a vacuum, not always in a vacuum actually, sometimes in air as well, because that has a cool effect as well, where you'd spray tiny microspheres of oil and watch how they react, and as they move, the spheres themselves become electrically charged, and so therefore they interact with the field that they're inside. And so he did a bunch of experiments where you could, by adjusting the voltage between the plates, he could overcome gravity, and so that the electric force up on these particles was equal to mg, and so the particles would hover, okay, in between the plates and not move. If he reduced that electrical force, and they'd start to fall, and if they fell, they would fall, and he would be able to measure their terminal velocity if they were falling through air. And if he ramped up the field, he could actually make them shoot the other way and actually find the top plate, completely overcoming gravity. So Millikan did a whole bunch of work on this. What you should do is, just out of interest, and because they do mention Millikan occasionally in questions, find yourself a couple of videos like Millikan's experiment, electric charges. Go off onto YouTube. Use it for good instead of evil, and find out some information about Millikan and really get it into your head just in case a question pops up saying, referencing Millikan as though you'd heard of the guy, right? All right, so that is basically what my explanation is, basically all this stuff. All right, so here, there's, oh God, there's always more, isn't there? All right, we're nearly there, okay? Linear accelerators. All right, again, here's another video for you that you have to find, okay? Maybe finding a sort of, you know, a basic explanation, a kid's explanation of the synchrotron, for example, that we have. It's a big particle accelerator, accelerates bunches of electrons. We've talked about it in class before. It accelerates electrons and gives them energy, and it's used as basically a giant light source. And the way it does that is it'll have does it have a diagram of it? No, it doesn't. Okay, there'll be a hot piece of metal. It's heated by being connected to some potential, and heating the metal causes electrons to jump off. And then what happens once the electrons are free is there's an anode attached nearby, and it's positively charged, and it attracts the electrons away and gives them a little bit of an initial velocity. And then another set of magnets are used to then pick up these electric charges and accelerate them to 99.99% of the speed of light. And they end up getting trapped inside a tube, and that tube shoots around, and it's used as a light source to do experiments. Anyway, so anytime they're talking about a LIMAC, what they're talking about there is an electron gun, okay? An electron gun is just that early part of the synchrotron, which picks up the electrons, liberates the electrons, picks them up, and then shoots them down a line, a straight line accelerator, LIMAC, right? Until they can be then captured and used, turned into the big, into the booster ring, and then to the storage ring. And if you watch a video, you'll know what the hell I'm talking about there. And there's no specific video, just find one. There's thousands of them, okay? So that's what they're talking about here, electrons that have been picked up and then accelerated through a voltage, which is, again, something I've already discussed when we were looking at the help sheet. Okay, so electrical potential energy is stored in an electric field, and an electric field exerts a force on charged particles. This can be used to increase their speed and kinetic energy. The field will do work on the charged particles. An electron will experience a force in the opposite direction to the field due to its negative charge. The electric force is given by F equals Q. See, all of this stuff you know. The work done is given by work done is equal to force. Now, sometimes I wrote Fx in the help sheet, but it's Fd. It's the same thing, distance travelled. If the force is constant from a uniform field, the change in kinetic energy is the work done. So usually you'll see this work being done when an electron is being accelerated by the field in between two plates. All right, so that you can say it's got a uniform field, and hence you can predict the amount of work done, with the kinetic energy that it has picked up on its way through. Work done, QED. Okay, work done is the kinetic energy. QED, where D is the distance between where the charge enters the field and then exits the field, all right? Okay, this has not been particularly useful in any of the 68 questions that you're supposed to do, all right? It's there just in case it does crop up somewhere, but it's on the help sheet as well, okay? Let's see, work done on a charge is also given by W equals, work done is equal to QV, and since V equals ED, we get QED. The simplest device is an electron gun, which produces electrons and then accelerates them. The same process is used in mass spectrometers, electron microscopes, synchrotrons, and the Large Hadron Collider, which does very different science to a synchrotron. All right, some resource, electric fields, again. Watch this guy, he's cool. And we are now up to the questions. All right, so that's the end of this part of the video, okay? Make sure that you've got yourself your help sheet, you organize it nice. Make sure, now I've drawn mine really big, okay? You can actually scrunch up so much of this into much less space, okay? Don't forget, there are 4 chapters. The first one was really just introduction. It didn't really give you that much new stuff. But so essentially you have 3 full chapters to get onto one help sheet, okay? You need to be working on it because I did not do all of this to have us all come back at the end of our quarantine period and have everybody go, oh man, I never really did it. Was that compulsory, was it? It's like, yeah, it was compulsory. Do the work now. Make sure you stay ahead of the game. That way VCAR starts mucking around and chopping things out of the courses to make it a bit easier. You are actually way ahead of the curve that way, all right? So, see you again soon for magnetic fields. That's right.